what was he drawing a picture of? Well, this is a picture of the blood vessels in your eye. Lowell had adjusted the Clark refractor in a particular way that made it function kind of as a giant ophthalmoscope, which meant that it was actually casting shadows of the blood vessels in his eye onto his retina. So, as Lowell felt that he was mapping the surface of Venus, he was really mapping the surface of his own eye, which is, it's poetic and remarkable. It brings us, though, to this observation, which is, one that I really have to give some credit to Alex Menzies here, because he's pointed it out, about the role of VR and how it can act as kind of a new telescope for us. See, when you look at these three amazing telescopes and all the other advances in telescopes ever made, I want to point out a very important component common to every one of them that has never been upgraded, and that is us, the human. The human observer is sort of this fixed part of this observational system. And so we better get comfortable with this component, because we can't change it, we can't replace it. The brain that we are stuck with evolved to make some very important distinctions that really have nothing to do with what these gentlemen are doing here. They have to do with things like this, and also this. Our brains and senses were evolved to keep us alive, not necessarily to study a distant planet and decide whether there were features on the surface of Venus. And when we're confronted with these pictures of another world taken out of context, without any points of reference that we're used to seeing in our natural world, we can fall into perceptual traps and make ridiculous judgments like this one. The core problem is that there is nothing natural about what Percival Lowell is doing here in terms of his brain and his senses. The brain was not designed or evolved to look at the universe or the world this way. And so we are constantly, as we use an instrument this way, forcing ourselves to make mental translations to make this still make sense for us. And that is a problem, because we're a species that can explore like this, and yet we're exploring like that. And this got us very excited. Astronomy, modern astronomy, has in really many ways made this even worse, because we've removed even the feeling that comes from turning a telescope with your hands to point it in different directions. And we put everything behind screens and keyboards. And so when it became time for us to start exploring the surface of Mars, we did it the same way, because there was really no other option. We explore Mars from behind a computer screen. Even though we know that the reality of Mars is this: far more rich, far more complicated detail. So we started working on ways to break through those boundaries. And this is some really early work we did in this area, where we took early Oculus units and stuck tracking balls on them with the Vicon Bonita in our lab, and started experimenting with what would it be like if we could engage the positional, somatosensory, and proprioceptive senses in the human brain, let people walk around on Mars. And it turns out remarkable things happen. I just mentioned we experimented with different ways of rendering, mixtures of 2D and 3D rendering. This is all several years old work now. But we found this, and this has become an important result for us. We did a study where we took members of the science teams on the Curiosity and Spirit and Opportunity Mars rover missions, and we asked them to complete a task with data acquired by the Curiosity rover. And what we found was that there was a dramatic, measurable, and statistically significant effect on their understanding of the vicinity of the data acquired by the Mars rover when they were wearing a head-mounted display. And I'll just go briefly into a little more detail on this diagram. So there are two kinds of error in the axes of this graph. The left vertical axis is angular error accumulated for a subject, and the x-axis there is the accumulated distance error. So high error or poor performance is in the top right-hand corner of that graph, and excellent performance or low error is in the bottom left-hand corner. So each one of those marks on the graph is one of our experimental subjects. The red X's are people using the official mission operations tool that we use every day to operate the Curiosity rover mission, which was built in my lab. And then those green circles are the performance of individuals using the head-mounted display who had had zero training with the technology. We brought them in, put it on their head, gave them about 30 seconds to look around, and told them to make a map of their surroundings. I want you to note that everybody was good at that without training, and I believe the reason for that is that we were effectively just asking them to be human. And that result, this result, sent us really out into the world to push this work along much more quickly. We have partnered with a lot of people on this journey. This is some work we did with the fine people at Sony Magic Labs. You're seeing here a more detailed 3D rendering. I apologize, this is one of those captures from inside a VR headset, so it has the distortion that comes with that. And then more recently, work with Microsoft and the HoloLens and a project that we call OnSite. And OnSite, our kind of latest effort in this area, has this simple goal, which is that we want scientists to work together on Mars while still being in their office. We want to bring the surface of Mars into their offices, let them explore Red Planet as geologists have learned to explore Earth. And the reason why we're excited about this is that we already know that humans are phenomenal explorers. We've been doing it as long as we've been humans. So if we can let people explore Mars in the same ways that they've learned to explore Earth, in the more natural way that virtual and augmented reality enables, then we think we can make them more effective. And we already have a small pilot group of scientists who are just starting to use this now in the operation of the Curiosity Mars rover today. It's early days, we have a lot more work to do to discover how to change our mission operational paradigm to one that uses a technology like this, but we're already on our way. This is a 3D rendering, this is what the terrain looks like in the on-site program. So Alex and the rest of the terrain team have come up with a way to build the most detailed and high fidelity 3D rendering of Mars that's ever been created. And it includes data from our orbiters, automatically combined with multiple locations of surface data acquisition to build one contiguous mesh, which then gets textured with data acquired from all those different rover locations. And at every spot on the terrain, we're automatically deciding which image from the rover would offer the highest spatial resolution for that location. So that's what produces this. You'll notice, for example, there's no rover in it because we can image the area underneath the rover because the rover acquired that data from another location. So this is the quality of the terrain that we have in that tool today. So I'm going to transition to Victor here now. We're thinking out there at Mars, right? Well, we have another vanguard of exploration within NASA, which is the human exploration. And we, in my lab, don't want to neglect that part either. So we've also been building some applications to support the space station as well.
Thanks, Jeff. Let's take a moment and imagine we're an astronaut. This is actually something that I do a little bit too often, I think. Actually, let's imagine we're this guy. This is astronaut Scott Kelly, and he's been in space for an entire year now. By the time he gets back, he'll have been in space for a collective amount of more than 500 days. That's more than any other human being that's been in space. And this is where he lives. Right above the curvature of the Earth lies the International Space Station, or ISS for short. Here he lives with 5 of his best friends from around the world in a space of, the size of a football field with a volume of about a 6-bedroom house. And there, they perform experiments looking down on Earth, and inside the zero-G environment, they perform dozens of experiments every single day. And for the past year, Scott Kelly himself has been an experiment. Now, the space station, with all its components and computers and electronics, the things that have to keep the astronauts alive, is perhaps the most complicated man-made machine that's ever been built. And these 6 people that operate it every single day are expected to keep it in tip-top shape. That's a very hard job to do. In the past, when it was a much simpler living space, and when the astronauts weren't expected to live there as much, they could do a lot of this training on the ground, train up everything that they needed to perform, and then memorize all that and perform it on station. But nowadays, with experiments that are 3 to 6 months long, to even a year out long, it's impossible to keep track of everything that they are expected to perform. So what do? Well, to close the gap, they literally have instruction manuals for every single procedure that they do on board. And not all these procedures are easy to understand. This is what an actual procedure on the space station looks like. And this is actually a procedure for what happens if there's a fire on board the space station. So you can imagine if there's an emergency going on and they have to stop and read this to figure out what to do next. It's kind of ridiculous to think about all the abnormal or uncommon things that might happen on board. But even just looking at a procedure like this, there's a lot of complexities involved. All these acronyms, all these components that you're expected to find, just understanding the context of what you're trying to experiment with, all the environments, all the pieces that you need to grab, is very taxing for the astronaut. They have to go grab all these pieces, and when they're actually performing the experiment, the distance that they cover between where they look at the procedure and where they operate the procedure is a very long distance. This is very time-consuming. So we looked at this, and we saw an opportunity. We got really excited. What if we could build, for the first time, an immersive remote guidance tool that could connect the ground control, mission control operators with the astronauts on board the space station, and in real time walk them through these procedures as if they were there, drawing tools and adding procedures, loading these things up as they were performing these procedures. And what if we could build this amazing tool on this unreleased commercial platform, certified for a zero-G flight, then dive underneath the water and certify for 2 atmospheric pressure and 100% humidity, and then change the entire ISS network to handle this real-time communication, and then manifest it on a commercial flight, all